This is SpaceTime Series 26, Episode 147, for broadcast on the 8th of December 2023. Coming up on SpaceTime, detection of one of the highest energy cosmic rays ever, pinpointing the source of Io's volcanic activity, and Ariane 6 completes its hot engine test firing. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Back in 1991, the University of Utah's Fly-Eye experiment detected the highest energy cosmic ray ever observed. Later dubbed the Oh My God particle, the cosmic ray's energy shocked astrophysicists. Nothing in our galaxy has the power to produce it. In fact, the particle even had more energy than was theoretically possible for cosmic rays travelling to Earth from other galaxies. Put simply, this particle should not exist. The Fly's Eye telescope array has since observed more than 30 other high-energy cosmic rays, although none have approached the Oh My God level energy. No observations yet have revealed their origin or how they're able to travel to Earth. Then, on May the 27th, 2021, the Fly's Eye telescope array detected what is now the second highest extreme energy cosmic ray ever recorded. At 2.4 times 10 to the 20 electron volts, the energy of this single subatomic particle is equivalent to dropping a brick on your toe from waist height. It's an amazing, head-scratching discovery. The Fly's Eye telescope array consists of 507 surface detector stations arranged in a grid that covers some 700 square kilometres near Delta, Utah in the state's western desert. The event triggered 23 detectors in the northwest region of the array, splashing across some 48 square kilometres. Its arrival detection appeared to be from the local void, a vast empty area of space bordering the Milky Way galaxy. One of the study's authors, John Matthews from the University of Utah, says the particles are so high energy they shouldn't be affected by galactic or extragalactic magnetic fields, so you should theoretically be able to point to exactly where they're coming from in the sky. But in the case of both the Oh My God particle and this new particle, there's simply nothing in that part of space that could generate such a powerful cosmic ray. The findings, reported in the journal Science, have concluded that this rare phenomenon might follow particle physics into unknown science. The researchers have named the second particle Amaterasu after the sun goddess in Japanese mythology. The Oh My God and Amaterasu particles were detected using different observational techniques. That confirms that while rare, these ultra-high energy events are indeed real. Interestingly, the two events appear to originate in different parts of the sky, and that could indicate a special feature in the structure of space-time, such as colliding cosmic strings. But that's just speculation, because in reality there's simply no conventional explanation for them. Cosmic rays are echoes of violent celestial events such as supernovae or feeding black holes. Essentially, cosmic rays are simply charged particles with a wide range of energies, usually consisting of positively charged protons, negatively charged electrons, or entire atomic nuclei that have travelled through space and nearly constantly rain down on the Earth. When they hit the Earth's upper atmosphere, they split apart the nucleus of oxygen and nitrogen gases, generating secondary particles. These travel a short distance in the atmosphere before repeating the process, building a shower of billions of secondary particles that rain down onto the surface. The footprint of the secondary shower is massive and requires detectors that cover a large area, which is what the Fly's Eye telescope array does. The surface detectors utilize a suite of instrumentation that gives researchers information about each cosmic ray particle, the timing of the signal shows its trajectory, and the amount of charged particles hitting each detector reveals the primary particle's energy. Because particles have a charge, their flight path resembles that of a ball in a pinball machine, as they zigzag against the electromagnetic fields through the cosmic microwave background. Usually, it's nearly impossible to trace the trajectory of most cosmic rays other than those coming from the Sun, because they lie on the low to middle end of the energy spectrum. Even high-energy cosmic rays are distorted by the microwave background. But particles with Oh My God and Amaterasu energy levels blast through intergalactic space nearly unbent. Only the most powerful celestial events could produce them. Things that people think of as energetic, like supernovae, are simply nowhere near energetic enough for this. Matthews says you need huge amounts of energy and really high magnetic fields in order to confine the particle while it gets accelerated. Ultra-high energy cosmic rays need to exceed 5 by 10 to the power of 19 electron volts. This means that a single subatomic particle carries 10 million times more energy than any human-made particle accelerator has ever achieved. Known source candidates, such as active galactic nuclei or black holes with accretion disks emitting particle jets, tend to be more than 160 million light-years from Earth. Researchers also analysed cosmic ray composition for clues to its origin. A heavier particle like an iron nuclei are more massive, have more charge, and are also more susceptible to bending in a magnetic field compared to lighter particles made of protons from hydrogen atoms. So the new particle is likely a proton. The Fly's Eye telescope array is uniquely positioned to detect ultra-high energy cosmic rays. It sits at about 1,200 metres, that's 4,000 feet in elevation, in a sweet spot that allows secondary particle maximum development before they start to decay. Its location in Utah's western desert provides ideal atmospheric conditions in two ways. The dry air is crucial because humidity will absorb the ultraviolet light necessary for detection, and dark skies are essential because light pollution will create too much noise, obscuring the cosmic rays. The telescope array is currently in the middle of a major expansion that they hope will help crack the case. Once completed, 500 new scintillator detectors will expand the telescope array's capacity, allowing it to sample cosmic ray-induced particle showers across some 2,900 square kilometres. This is SpaceTime. Still to come, pinpointing the source of Io's volcanic activity, and Europe's new Ariane 6 rocket successfully completes its engine hot fire testing. All that and more still to come on SpaceTime. The Jovian Moon Io is the most volcanically active place in our solar system. Whereas in normal worlds you'd have weather reports with rain in the east and sunny conditions in the west, on Io you'd be relying on volcanology reports with lava flows in the east and mega eruptions in the west. Now, a new study suggests that most of the Jovian Moon's tidal heating is concentrated within its upper mantle. The findings, reported in the journal Nature Astronomy, are based on detailed observations of heat emissions and volcanic activity on a global scale. Io's surface is covered with caldera as well as flowing rivers of molten rock. It's all caused by gravitational tidal heating generated by the Moon's elliptical orbit around Jupiter in combination with the orbits of some of the other nearby moons. This causes little Io to constantly stretch and squeeze, generating friction in its rocky interior. It's the same heating effect you'll get if you bend a paperclip backwards and forwards very quickly. So, scientists know how Io gets its heat, but they don't know exactly where the heat's originating. Is it deep within the Moon or closer to the surface? The evidence now suggests the latter. Most of the data regarding heat emissions from Io have been focused on the Moon's equator. But in 2016, NASA's Juno spacecraft began orbiting Jupiter around its poles, and that's given scientists a new perspective on Io by examining heat emissions from its poles. Scientists combined the new data with previous observations to create a new global heat map of the little Moon. They were able to map some 266 volcanic hotspots and found that the Moon was emitting 60% more heat from its lower latitudes than from its more polar regions. That suggests the heat responsible for much of the volcanic activity on Io is located just below the surface rather than deeper down. And it could also mean Io has a soft upper mantle, or maybe even a molten magma or ocean beneath its crust. This is SpaceTime. Still to come, Ariane 6 successfully completes its hot fire engine test, and the December solstice, the ticking time bomb that is Eta Carinae, and the rock comet Phaethon are among the highlights of the December night skies on Skywatch. The European Space Agency's new Ariane 6 launcher has successfully completed a key engine firing test in preparation for next year's maiden flight. The full hot fire engine burn at the European Space Agency's Kourou spaceport in French Guiana simulated a complete launch sequence, which involves the Ariane 6's Vulcan 2.1 main engine lighting up for over 7 minutes. The engine hot test is a key milestone in the rocket's development. Only a few additional fault tolerance tests now need to be carried out in order to validate the core stage ready for flight. The hot fire engine burn had been delayed several days due to a problem with the hydraulics in the main engine's thrust vectoring control system. In fact, the entire Ariane 6 program has been running years behind schedule. Its first flight was originally slated for 2020, but it was delayed several times due to both the COVID-19 pandemic and also a string of technical issues. ESA and Arianespace need the new rocket ready for flight as soon as possible. Its predecessor, the Ariane 5, blasted off for its last mission back in July, following 27 years of service. And the smaller Vega C rocket remains grounded following a launch failure last December. Adding to Europe's problems, the Kremlin's invasion of Ukraine has triggered sanctions by the West on the use of Russian rockets and equipment, putting a halt on Soyuz launches from Kourou. All that has left Europe without an independent means of getting to orbit until the Ariane 6 is ready. We'll keep you informed. This is SpaceTime. Time now to turn our eyes to the skies and check out the night skies of December on Skywatch. December is the 12th and final month of the year in both the Julian and Gregorian calendars. Its name comes from the Latin word decim, meaning 10, because it was originally the 10th month of the year in the old Roman calendar, which began in March. Of course, the astronomical highlight of the month is the December solstice, which this year occurs at 14:27 Australian Eastern Daylight Time on the afternoon of Friday, December the 22nd. That's 10:27 in the evening on Thursday, December the 21st, US Eastern Standard Time, and 3:27 in the morning of Friday, December the 22nd, Greenwich Mean Time. The December solstice is when the sun appears to reach zenith directly over the Tropic of Capricorn. In the United States and most of the Northern Hemisphere, it marks the winter solstice, signifying the first day of winter. But the good news is that from now on the days start to get longer again. South of the equator, summer has well and truly arrived, and the days are usually at their warmest. The seasons occur because of a tilt in Earth's spin axis, which is inclined at 23.4 degrees in relation to the Sun. Now, generally speaking, Earth's axis always appears to point at the same position in space, regardless of the position of the Earth in its orbit around the Sun. So on the day of the December solstice, Earth's south pole is tilted directly towards the Sun, so the southern hemisphere gets more daylight and consequently more direct sunlight, so it's hotter and it's the southern hemisphere summer. 6 months later, during the June solstice, the northern hemisphere is tilted towards the sun, and so it's the northern hemisphere which experiences summer, while the southern hemisphere gets less daylight, longer nights, and the sunlight strikes the surface at a shallower angle, meaning less heat, and consequently it's the southern hemisphere's winter. In between these, we have the March and September equinoxes. That's when the northern and southern hemispheres get roughly equal amounts of daylight and heat, in the process giving us the seasons of spring and autumn. Now earlier we said that generally speaking, Earth's axis always points to the same position in space regardless of Earth's orbital position around the Sun. And while that's true in our day-to-day lives, over geologic time, a gravity-induced effect known as axial precession causes a slow and continuous change in the orientation of Earth's rotational axis. You can see the same effect in the precession of a spinning top as the axis traces out a pair of cones joined at their apses. Earth's precession is known as the precession of the equinoxes. That's because the equinoxes move westwards along the ecliptic relative to the fixed background stars. This slow precession means that over 25,772 years, the positions of the north and south celestial poles appear to move in circles against the space-fixed backdrop of stars. So, while today the star Polaris lies approximately at the North Celestial Pole, this will change over time, with Gamma Cephei becoming the North Star in about 3,200 years. It also means the seasons would slowly move into different calendar months. But of course we make adjustments for this in the calendar to compensate. In most parts of the world, the seasons begin on the day of the solstice or equinox. However, Australia follows meteorological seasons, which begin on the first day of a particular calendar month. The 1st of March for autumn, the 1st of June for winter, September the 1st for spring, and the 1st of December for summer. Because of the relatively small amount of elongation in Earth's orbit around the Sun, Earth's seasons are determined by its axial tilt rather than its orbital distance from the Sun. Now currently, Earth's closest orbital position to the Sun, perihelion, occurs about 2 weeks after the December solstice, and it's furthest from the Sun at aphelion about 2 weeks after the June solstice. That means the next perihelion will occur on Wednesday, January the 3rd at 11:38 a.m. Australian Eastern Daylight Time, when the Earth will be 147,100,632 kilometres from the Sun. That's 7:38 in the evening of Tuesday, January the 2nd, US Eastern Standard Time, and 38 minutes after midnight on Wednesday, January the 3rd, Greenwich Mean Time. Like axial precession, the Earth's orbit also changes gradually over geologic timescales, getting more or less elongated and changing perihelion and aphelion. Even the degree of tilt of the Earth's spin axis changes over thousands of years. Now collectively, these are all known as Milankovitch cycles, after the Serbian geophysicist and astronomer Milutin Milankovitch, who in the 1920s hypothesized that variations in eccentricity, axial tilt and precession resulted in cyclical variations in solar radiation reaching the Earth, and that this strongly influenced Earth's climatic patterns. Okay, let's start our tour of the night skies in the west, where midway up from the horizon you'll find Fomalhaut, the brightest star in the constellation Pisces Austrinus, the southern fish. Fomalhaut is a young white spectrotype A main sequence star, about 1.8 times the diameter of the Sun, located about 25 light-years away. A light-year is about 10 trillion kilometres. The distance a photon can travel in a year at 300,000 kilometres per second, the speed of light in a vacuum, and the ultimate speed limit of the universe. Main sequence stars are those undergoing hydrogen fusion into helium in their core. Astronomers describe stars in terms of spectral types, classification system based on temperature and characteristics. The hottest, most massive and most luminous stars are known as spectral type O blue stars. They're followed by spectral type B blue-white stars, then spectral type A white stars, spectral type F whitish-yellow stars, spectral type G yellow stars, that's where our Sun fits in, spectral type K orange stars, and the coolest and least massive stars known are spectral type M red stars. Each spectral classification is also subdivided using a numeric digit to represent temperature, with 0 being the hottest and 9 the coolest, and a Roman numeral to represent luminosity. Now put all that together and our Sun is officially classified as a G2V or G25 yellow dwarf star. Also included in the stellar classification system are spectral types L, T and Y, which are assigned to failed stars known as brown dwarfs, some of which were actually born as spectral type M red stars, but became brown dwarfs after losing some of their mass. Brown dwarfs fit into a unique category between the largest planets, which are about 13 times the mass of Jupiter, and the smallest spectral type M red dwarf stars, which are about 75 to 80 times the mass of Jupiter, or about 0.08 solar masses. In 2008, astronomers detected planets orbiting around Fomalhaut. It's not known if anyone was looking back. 5,000 years ago, the ancient Mesopotamians used Fomalhaut to mark the northern hemisphere's winter solstice. Turning to the left of Fomalhaut, you'll find the star Achernar Alpha Eridani, the brightest star in the constellation of Eridanus the river. Located 139 light-years away, Achernar has about 7 times the diameter of the Sun and rotates some 15 times faster, giving it an oblate shape. The effect of this rapid rotation is that the star flattens at the top and bottom, but bulges in the middle. In fact, its equatorial diameter is around 50% greater than its polar diameter. Achernar is actually a pair of multiple star systems, Alpha Eridani A and Alpha Eridani B. The primary star, Alpha Eridani A, is a hot blue spectral type B main sequence star. Its smaller companion, Alpha Eridani B, is a spectral type A white star. The pair orbit each other at a distance of about 12 astronomical units. An astronomical unit is the average distance between the Earth and the Sun, about 150 million kilometres or 8.3 light minutes. Moving further left from Ekarina, and just above the horizon this time of year, is Canopus, the brightest star in the southern constellation of Carina the Keel, and the second brightest star in the night sky after Sirius. Canopus is a white giant, nearing the end of its life, and located about 310 light-years away. It has about 8.5 times the mass of the Sun, but has now expanded out to about 71 times the Sun's diameter. Canopus is hard to miss. It has some 1,300 times the brightness of the Sun and is in fact the brightest star within 700 light-years of Earth. Its name originates in mythology from the time of the Trojan Wars and the navigator for Menelaus, king of Sparta. Located between Canopus and the Southern Cross in Carina, in the Trumpler-16 open star cluster, is the ticking time bomb known as Eta Carinae. Eta Carinae is a pair of huge blue stars undergoing the violent final phase of their existence before exploding in massive core collapse supernovae. The binary system, located some 8,500 light-years away, is buried deep inside the giant nebula of Carina, a massive cloud of gas and dust between 6.5 and 10,000 light-years away. The stars in Eta Carinae are both classified as highly luminous spectral type O blue hypergiants. Its primary star is huge, estimated to be between 150 and 250 times the mass of our Sun, with around 5 million times the Sun's luminosity, 800 times its radius, and a surface temperature of some 32,500 Kelvin. This is the only star known to produce ultraviolet laser emissions. And astronomers estimate it's already lost some 30 times our Sun's mass. The companion star, although smaller than the primary, at just 30 to 80 solar masses and 20 times the Sun's radius, is even hotter, with a surface temperature of around 37,200 Kelvin. The two stars orbit each other every 5.54 Earth years, cocooned in a thick twin-lobe cloud of gas and dust known as the Homunculus Nebula, a spectacular bipolar emission and reflection nebulae. The nebula was created when Eta Carinae underwent a spectacular eruption starting in 1837. Known as the Great Eruption, it eventually reached its peak in 1843, by which time it was one of the brightest objects in the night sky, almost as bright as Sirius, before gradually fading away again by 1856. Eta Carinae underwent another significant but smaller eruption in 1892, and it's again been getting steadily brighter since 1940. Both Eta Carinae and its surrounding shroud of dust generate huge amounts of infrared radiation, making it the brightest infrared source in the sky. Both stars are nearing the end of their lives on the main sequence and are expected to go supernova in an astronomically short space of time. When it does so, Eta Carinae will be easily visible in daylight and may even become brighter than the full moon for months on end. No one knows exactly when Eta Carinae will go supernova. It could be tonight, or it could be in 1,000,000 years from now. A single star, originally around 150 times as massive as the Sun, would typically reach core collapse as a Wolf-Rayet star within, say, 2 to 3 million years. At low metallicity, many massive stars would collapse directly to form a black hole, with no visible explosion at all, or a subluminous supernova at most. And a small fraction will produce what's known as a pair instability supernova. But at solar metallicity and above, there's expected to be enough mass loss before collapse to allow a visible supernova to occur. By the way, that term metallicity, well, astronomers regard all elements on the periodic table to be metals other than the hydrogen and helium created in the Big Bang 13.82 billion years ago. Highly massive progenitor stars could also eject sufficient nickel to cause a superluminous supernova simply from radioactive decay. And the resulting remnant would be a black hole, since it's highly unlikely that such a massive star could ever lose sufficient mass for its core not to exceed the limits of a neutron star, somewhere around 2.2 to 2.4 times the mass of the Sun. But the existence of a massive companion star in Eta Carinae brings many other possibilities into consideration. For example, if Eta Carinae A was rapidly stripped of its outer layers, it might become a less massive WC or WO type star when core collapse was reached. And this would result in a Type 1b or Type 1c supernova due to the lack of hydrogen and possibly helium. and these supernovae are thought to be a possible originator for some types of gamma-ray bursts, generally regarded as the most powerful explosions in the universe since the Big Bang. Several unusual supernovae and imposters have been compared to Eta Carinae as possible examples of this fate. One of the most compelling is SN2009 IP, a blue supergiant which underwent a supernova imposter event in 2009, with similarities to Eta Carinae's Great Eruption. Then an even brighter outburst occurred in 2012, which is likely to have been that star's true supernova. Still, the most likely theory for Eta Carinae's ultimate fate would be collapsing to form a stellar mass black hole, with the energy released as jets along the axis of rotation as gamma-ray bursts. A typical core collapse supernova at the distance of Eta Carinae would look every bit as bright as Venus in the sky. And remember, only the Sun and Moon are brighter. A superluminous supernova could be 5 magnitudes brighter, potentially the brightest supernova in recorded history. The good news is Eta Carinae is not expected to produce a gamma-ray burst, and its axis isn't currently aimed anywhere near the Earth. At 7,500 light-years from the star, it's unlikely to directly affect terrestrial life on Earth when it does blow, thanks primarily to our planet's atmosphere and magnetosphere. But the ozone layer could be damaged, as with any orbiting spacecraft and astronauts in space at the time. And at least one paper has projected that complete loss of the Earth's ozone layer is a plausible consequence of a supernova, which would result in a significant increase in ultraviolet radiation reaching the Earth's surface from the Sun. But this would require a typical supernova to be closer than 50 light-years from Earth, and even a potential hypernova would still need to be closer than Eta Carinae. Another analysis of possible impact discusses more subtle effects from the unusual illumination, such as possible melatonin suppression, with resulting insomnia and an increased risk of both cancer and depression. Okay, enough gloom and doom for now. Let's turn to the east, and looking just above the horizon is the star that outshines Canopus to take the title of the brightest star in our night sky, Sirius the Dog Star. And next to it, in the east-northeastern skies, just above the horizon, is the constellation of Orion the Hunter. Now, if you look closely, you'll see a very bright red star. That's the supergiant Betelgeuse, better known to most people these days as Betelgeuse. Don't say it 3 times. In ancient times, before centuries of mispronunciation, the name started out as Isbet al-Yauza. Betelgeuse is one of the largest and most luminous stars visible to the unaided eye. Located some 430 light-years away, this bloated old red supergiant is nearing the end of its life. And it's truly massive. Some 1,100 times the diameter and 100,000 times the brightness of our Sun. Like Eta Carinae, Betelgeuse is destined to explode as a core collapse supernova sometime in the near future. Betelgeuse marks the right shoulder of Orion the Hunter, although it's all upside down from the perspective of anyone in the southern hemisphere, as Orion was a hunter in Greek mythology, so the constellation was viewed from the northern hemisphere. The earliest depiction that has been linked to the constellation of Orion is a prehistoric mammoth ivory carving found in a cave in the Acht Valley in West Germany in 1979. Archaeologists have estimated that it was fashioned sometime between 32 and 38,000 years ago. The distinctive pattern of Orion has been recognized in numerous cultures around the world, including the ancient Babylonian star catalogues dating to the late Bronze Age. In Greek mythology, Orion was a gigantic, supernaturally strong hunter of ancient times. He was the son of a Gorgon and Poseidon, also known as Neptune, the god of the sea in the Greco-Roman tradition. One day, the goddess Gaia became enraged at Orion after he boasted that he would kill every animal on Earth. So she sent a scorpion to sting Orion to death. However, Ophiuchus the serpent-bearer revived Orion with an antidote. This is given to be the reason that the constellation Scorpius chases Orion across the sky, with the constellation Ophiuchus standing midway between them. The other major stars in Orion include Rigel, Orion's left foot. It's a blue supergiant. Having exhausted its core hydrogen, Rigel's now swollen out to between 79 and 115 times the Sun's radius, and it's fusing heavy elements in its core, meaning it too will soon likely go supernova, eventually collapsing to form a neutron star. Rigel's estimated to be somewhere between 120,000 and 279,000 times as luminous as the Sun. And it's a binary system located 860 light-years away. Its companion star, Rigel B, is some 500 times fainter than the supergiant Rigel A, and it's only visible through a telescope. But Rigel B itself is a spectroscopic binary system comprising of two main sequence blue-white stars. Spectroscopic binaries are double star systems orbiting each other in such a way that they can only be visually separated from our vantage point here on Earth by their different spectroscopic signatures. The two stars making up Rigel B are estimated to be 3.9 and 2.9 times the mass of our Sun, respectively. And one of these stars, Rigel BB, may itself be a binary. And Rigel B also appears to have a very close visual companion, Rigel C, of almost identical appearance. The third brightest star in Orion is Bellatrix, Orion's left shoulder. It's a spectrotype B main sequence blue star with about 8.6 times the mass and 6 times the radius of the Sun. Bellatrix is located some 250 light-years away. It's estimated to be about 25 million years old. That's enough for a star of this mass to have consumed most of the hydrogen in its core and begin to evolve away from the main sequence into a blue giant. Now, if you look at the 3 stars which make up Orion's belt, you'll see another 3 stars which make up Orion's sword hanging from the belt. If you look carefully at the middle star, you'll notice it's a bit fuzzy looking. That's because it's not a star, it's the Great Nebula of Orion, Messier 42. Located just 1,344 light-years away, M42 is the nearest massive star-forming region to Earth. The M42 Nebula is estimated to be about 24 light-years across and has a mass of over 2,000 suns. The Orion Nebula is one of the most scrutinized and photographed objects in the night sky, and it's among the most intensely studied celestial features. In fact, the nebula has revealed much about the process of how stars and planetary systems are formed from collapsing molecular gas and dust clouds. By studying M42, astronomers have directly observed protoplanetary disks, brown dwarfs, tense and turbulent motions of gas, and the photoionizing effects of massive nearby stars in the nebula. The Orion Nebula contains a very young open star cluster known as the trapezium due to the asterism of its 4 primary stars. And the trapezium is a component of the much larger Orion Nebula cluster, an association of about 2,800 stars within a diameter of just 20 light-years. One of the most stunning nebulae in the constellation Orion is the spectacular Horsehead Nebula, Barnard 33. The Horsehead is a dark nebula located just south of the star Alnitak, which is the furthest east on Orion's belt, and is part of the much larger Orion Molecular Cloud Complex. Located around 1,500 light-years away, the Horsehead Nebula was first recorded in 1888. It's one of the most identifiable nebula because of the shape of its swirling cloud of dark dust and gases, which bears a remarkable resemblance to a horse's head when viewed from Earth. One of the astronomical highlights of December is the annual Geminids meteor shower, which usually peaks around December the 13th and 14th. Radiating out from the direction of Gemini, the Geminids are unusual in that they're not generated by a comet as most other meteor showers are, but are produced by the debris trail left behind by the asteroid 3200 Phaton. This makes the Geminids, together with the Quadrantids, the only major meteor showers not originating from a comet. 3200 Phaton is highly unusual. Its high orbital eccentricity more closely resembles that of a comet than an asteroid. And in fact, it may be an asteroid that's simply run out of the volatile gases that characterize a comet. Phaeton's orbit crosses all the inner terrestrial planets, Mercury, Venus, Earth and Mars. It'll make its closest approach to Earth on December the 14th, 2093, when it will pass just 2,960,000 kilometers from Earth. The 5-kilometer wide asteroid is classified as potentially hazardous. Interestingly, Phaeton's named after the son of the Greek sun god Helios. Legend has it that Phaeton almost destroyed the Earth by stealing Helios's chariot and scorching the Earth with the sun, almost causing the apocalypse. Phaeton approaches the sun closer than any other named asteroid, with a perihelion of less than 21 million kilometers. That's less than half of Mercury's perihelion distance. Coming so close to the sun causes its surface temperature to reach over 750 degrees Celsius, and observations by NASA's Stereo spacecraft have observed dust trails radiating off its surface. In fact, in 2010, Phaeton was seen ejecting dust. Now, scientists think the intense heat generated by its close approach to the Sun is causing fractures in gravel and rocks on the asteroid's surface, similar to mud cracks in a dry lake bed. Phaeton's composition also fits the notion of a cometary origin. It's classified as a B-type asteroid because it's composed of dark material. And B-type asteroids are thought to be primitive volatile rich remnants of the early solar system. Its composition, orbit and dust trail have all combined to lead astronomers to refer to Phaeton as a rock comet. The Geminids meteors it produces have a yellowish hue to them, and they tend to be a bit larger and more solid than typical meteors from comets. They also move more slowly, travelling at around 35 kilometres per second, compared to some cometary meteor showers, which travel at speeds of up to 72 kilometres per second. And interestingly, the Geminids are thought to be intensifying every year, with recent showers seeing up to 160 meteors per hour under optimal conditions. In the Northern Hemisphere, expect to see up to around 120 meteors per hour between midnight and 4 a.m, but only from a dark sky. Now, well north of the equator, the radiant rises about sunset, reaching a usable elevation from local evening hours onwards. In the Southern Hemisphere, you won't see as many meteors, perhaps just 10 to 20 an hour. That's because the radiant doesn't rise above the horizon. Now, also for listeners in the Northern Hemisphere, there's a second meteor shower in December, the Perseids, which radiate out from Ursa Minor, the Little Dipper. The Perseids are generated by debris left behind by the comet 8P Tuttle. They're a compact stream, peaking on the night of December the 22nd and the early morning hours of December 23rd. Just look towards the bowl of the Little Dipper, and you might see about 10 meteors an hour. And now, with the rest of the December night skies, we're joined by Jonathan Nelly from Sky and Telescope magazine.
G'day, Stuart. Yeah, it's December, so it's now officially summer where I live in the southern half of the planet. We go on the sort of month arrangement rather than the solstice and equinox arrangement. So for where I live, summer is December, January, February, so it's now officially summer, and that's really, really good. So even though the hours of daylight are longer, so we have fewer hours, technically speaking, to do some stargazing, the weather's better, so that sort of makes up for it, because during wintertime, if it's cloudy or whatever, you're not getting much done anyway. So summertime weather, you usually get a lot of good stargazing in. And what sort of stargazing we've got? If we look out to the east in the middle part of the evening, we'll see Stuart's favourite constellation, which is Orion the Hunter. In fact, lots of people love Orion. It is really quite specky. I remember sweeping through its sort of star fields with a small pair of binoculars when I was a teenager, just learning my way around the sky. So there's lovely warm summer evenings and just seemingly endless stars and nebulae and star clusters and things to see. It was just magical. Orion is a really magical area of the sky if you get a pair of binoculars onto it.
Well, I like it because it's a series of guide stars. From there, I know where I am in the sky and I can work my way around to other constellations. And it's the same with the Southern Cross. If I can spot the Southern Cross, again, I know where I am.
And the good thing about Orion is that it straddles the celestial equator. So, through the middle of Orion, there are three stars in a sort of tight row next to each other, and that's Orion is the Hunter. So those three stars in a row are the Hunter's belt, and you've got a bright star to the north of it, and you've got a bright star to the south of it. You've got Rigel and Betelgeuse. But because it straddles the equator, when Orion is up in the sky, you know where the equator is in the sky, you know where north is, you know where south is. Everyone can see it. When it's up in the sky, everyone can see it from both hemispheres. It's not like it's stuck way down in the south or way up in the north, so a lot of people miss out because it straddles just happens to straddle directly over the equator. So you really can't miss it. That's another really good reason for looking at Orion, because it's always up nice and high in the sky for most people. Around to the sort of north of Orion, you should see a reddish star that's in one corner of a wedge of stars. The star is called Aldebaran, and the wedge of stars is an open star cluster called the Hyades, or Hyades. The Hyades is about 150 light years away, which is pretty close, really, in space terms, and it looks really fantastic through a pair of binoculars, too. If you get your binoculars and you make sure they're adjusted so you've got them in really nice focus, you see these beautiful pinpoint bright stars. And if you think the Hyades are good, then there's an even better star cluster a little bit further around to the west from that, and this is called the Pleiades, which is also known as the Seven Sisters. So called because many people, perhaps most people, when stargazing from dark skies, and when you let your eyes adapt to the darkness, you should be able to make out 7 of its stars just with the unaided eye. Some people, I think, have claimed up to 12 if they've got really good eyesight. It actually has about 1,000 stars in it, but you're not going to see all of those, of course, unless you've got a telescope. But even binoculars onto that, it just looks magical, absolutely magical. And if you have a Subaru car or you see a Subaru car go past, have a look at the emblem, the badge on the front of it. You'll see it's a little group of stars. That is the Pleiades, the Seven Sisters, because in Japan it's called Subaru. That's their name for it.
It's amazing the way all over the world this group of stars, it's not a constellation, it's just a group of stars, are known as the Seven Sisters or Seven Women. It doesn't matter if you're in Europe or Africa or Australia, Northern Asia, even the Americas, it's still seven women, seven sisters. And in many cultures, they're being chased by Orion the Hunter.
Yeah, they might not call him Orion, but he's someone who's chasing these things. Yeah, it is quite interesting how these sort of mythologies have just sort of built up and the way the human mind works. But you're quite right. Yeah, the Seven Sisters is known as Seven Sisters in all sorts of different languages from all different parts of the world.
It's amazing. Yeah, what's Greek mythology in Europe is Australian Aboriginal mythology down under. It's exactly the same story.
Yeah, it's wonderful stuff. It's just the way the human mind works and the sort of mythologies and legends we come up with back in those days when they saw these things in the sky. Now, of course, we just know them as great big balls of hydrogen gas and helium gas burning away thousands and thousands of light years away, which sort of ruins the poetry of it a bit, but I don't think it does.
Well, there's still some mystery with Pleiades because we can't
exactly
work out how far away it is. No.
That's right, yeah. There's a bit of a range of estimates of distance for that one, but... One day they'll probably figure it out. But anyway, back to the skies. So we've been up at the north. Let's go down the south, the far southern skies. This time of the year, we've got the Southern Cross, which is upside down. And for someone where I live in Sydney in Australia, it's not only upside down, but it's basically half obscured below the horizon. It's below the house across the road. I can't really see the Southern Cross. In the sort of
you can't get more local in a description than that, can you, really?
Just across the road there,
That's
exactly, yeah.
Cool.
Well, this is the thing. I think a lot of people would probably assume that you can see the Southern Cross all the time, right?
Yeah.
And look, if you go far enough south, then yes, you can see Southern Cross all the time. When you're far enough south or north, in the northern hemisphere, that you can see a constellation that is sort of getting close toward the celestial pole, and you can see it all the time, all year round. They call that circumpolar. It's always visible. So from Sydney here, the Southern Cross is not circumpolar, or a couple of its stars are, but not its entirety. You go down to Melbourne and you can see it. You go down to Tasmania, bottom of New Zealand, bottom of South America, you'll always be able to see the Southern Cross. It might be low down towards the horizon, but you can always see it all year round. But for me, this is not a good time of year to see the Southern Cross. Unless you leave it later in the evening. If you're out past midnight, then the Earth will have turned on its axis, and so the cross will have swung up from down on the horizon, and it'll be out towards the sort of southeast, and you will be able to see it quite easily. It'll be sort of sitting on its side. But yeah, I think a lot of people think you can see the Southern Cross all the time, but you really can't, depending on where you are. Now, what else have we got? So two things you can see easily at this time of the year down the south are the two nearest sizable galaxies to our own, the large and small Magellanic Clouds, named after Ferdinand Magellan. These are nice and high directly to the south in December, and they look just like faint, fuzzy clouds, but they are in fact galaxies full of millions of stars. Now, to see them, you're going to need to get away from street lights and other sources of light pollution, like your back door light or your front door light or whatever. Just get away from as many lights as you can and allow your eyes to dark adapt and have a look deep into the south, sort of halfway up or a bit more from the horizon, and you should see these two fuzzy clouds, the Magellanic Clouds, and they are actual galaxies, which is pretty amazing when you think about it. It's one of the reasons why a lot of really good astronomy gets done in the southern hemisphere, because they are the two closest prominent galaxies to us, the Milky Way, so they're good, test beds, I suppose, or trials. If they want to study what's happening in other galaxies, they're the ones to see. Same thing with looking into the centre of our galaxy. The centre of our galaxy is located in the southern skies for people here on Earth, so there's a lot of interest in the centre of our galaxy as well. So down here is the best place to look at it from, or from which to look at it. Now let's take a look at the planets. If you want to see Mercury, you'll need to do so in the first week or two of December, because it starts the month above the western horizon after sunset, looking just like a small bright star. But after the first week, it's going to start dropping down towards the horizon and will soon disappear from view. And it'll depart from our evening skies, and it will turn up later in our morning skies out to the east. Out to the east at the moment, you've got Venus, which is a very prominent morning object, and you'll be able to see it if you get out of bed when it's still dark, or if you've pulled an all-nighter and you're on your way home, a couple of hours before dawn. You should be able to see this big, bright white light in the eastern sky. You can't miss it, really. Just look to the east, find the brightest looking star-like thing, and that's Venus. Mars, which is a very popular planet all the time, cannot be seen at the moment. Hasn't been seen for a while, actually, because it's around the other side of the sun from us. So it's lost in the solar glare. It'll come back into our morning skies in January. Interesting thing about when Mars or any other planet that has spacecraft from Earth orbiting it or on its surface, when they're around the other side of the planet, you can't get radio signals through. Jupiter, the biggest planet of the solar system, it can be seen after sunset in the northern part of the sky for southern observers, or in the southern part of the sky for those in the northern half of the planet. It's quite bright, so you really shouldn't have any trouble spotting it because it's the brightest star-like thing in its area of the sky at the moment. But if you are having trouble identifying which one it is, go out on the evening of December the 22nd and you'll see the moon with what looks to be a bright star very nearby. Well, that is actually Jupiter. The path that the moon takes through the sky brings it basically close to, in line of sight terms, close to each of the planets in turn over the course of a month. So every now and then it just lines up that the moon will be close to Jupiter, or it might be close to Mars or one of the other ones. And in fact, Saturn is going to be doing the same thing. So Saturn can be found about halfway up from the western horizon after sunset during December. And it too is quite bright, and it's got a sort of yellowy tinge. But if you're having trouble identifying it, have a look on the 17th and 18th of December, because the moon will be close by. On the 17th, the moon will be on one side of it, and the 18th, the moon will have moved in its orbit a little bit more, so it'll be on the other side of the star. And of course, all these things I'm talking about are line of sight effects. The moon is very close to Earth. These planets are a long way away, so it's just things happening to line up from our line of sight from here on planet Earth. And that, Stuart, is what's in the sky for December.
That's Jonathan Nelly from Sky and Telescope magazine. And that's the show for now. SpaceTime is available every Monday, Wednesday and Friday through Apple Podcasts, iTunes, Stitcher, Google Podcast, Pocket Casts, Spotify, Acast, Amazon Music, Bytes.com, SoundCloud, YouTube, your favorite podcast download provider, and from spacetimewithstuartgary.com. SpaceTime's also broadcast through the National Science Foundation on Science Zone Radio and on both iHeartRadio and TuneIn Radio. And you can help to support our show by visiting the SpaceTime store for a range of promotional merchandising goodies, or by becoming a SpaceTime patron, which gives you access to triple-episode commercial-free versions of the show, as well as lots of bonus audio content which doesn't go to air, access to our exclusive Facebook group, and other rewards. Just go to spacetimewithstuartgary.com for full details. And if you want more SpaceTime, please check out our blog, where you'll find all the stuff we couldn't fit in the show, as well as heaps of images, news stories, loads of videos, and things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, through our SpaceTime YouTube channel, and on Facebook, just go to facebook.com/SpaceTime with Stuart Gary.
You've been listening to SpaceTime with Stuart Gary. This has been another quality podcast production from Bytes.com.